In this video, we'll move into Chapter 5, which discusses analytical trigonometry, and specifically we'll get into Section 5.1, which talks about verifying trig identities. But just one moment talking about just the big picture of Chapter 5. Through Chapter 4, we've gotten through a lot of what we consider the basics of trig. The definitions, the right triangle facts, the basics of the graphs. So we've covered the functions a lot in general, and we've, reminded ourselves of the idea of a function, the input-output relationship, especially when we got to the inverse trig function. But now as we move into Chapter 5, we have to realize that there's still a lot of algebra that we can do with the trig functions. We still have to talk about solving equations, how we treat them just the same way we treat algebraic functions, and how we could factor and cancel and do similar things. But especially because of the nature of the definitions of the trig functions, there are just literally lots and lots of identities. So that's where we start, everyone. The big picture in Section 5.1 is that we will verify trig identities, and I'll fully explain what that means in a moment. But first thing, we have to discuss what we should already know. And right here, I basically have the facts, the most essential facts that we're going to need to go through this section. That the nature of these relationships, that all the trig functions can be written in terms of sines and cosine. That's going to be a major component of what we try and do. But then also, we've got a few other known facts. We developed this and called it the Pythagorean trig identity way back at the beginning of the trig facts section. And we haven't really seen exactly what it does to this point. Now we're going to start seeing a lot more of its uses. But not only this, if you go in the book, the very beginning of Chapter 5, they list these facts and they even list some more. They remind us about sine being an odd function, cosine being an even function. So I'm minimizing our list a little bit. But coming to this, they list two other identities right alongside this one and realize they're already making new identities by using one we already have and other ideas. So take this identity and let's divide everything. Let's start by dividing everything by cosine squared. Sine squared divided by cosine squared. Well, tangent is sine over cosine. They're both squared, so sine squared divided by cosine squared will end up giving me tangent squared. Plus, now I'll do cosine squared divided by cosine squared. Remember, I can't just do one piece or of one side. I have to do everything in the entire equation. So cosine squared divided by cosine squared, that just equals 1. And then last, 1 divided by cosine squared. Well, 1 divided by cosine is secant, so 1 divided by cosine squared is secant squared. That's another one of the identities that they give you, that they list for you. This one, if we remember it, it'll come in handy. But again, it's closely related enough that for our problems, knowing this one will be enough. But now let's take another look at that. And now let's divide that same original Pythagorean trig identity. But now let's divide everything by sine squared. Remember, everybody, this is trying to demonstrate that really sine and cosine are really our two main trig functions. And it kind of all boils down to those two. So this identity started with those original two. By dividing by cosine squared, we got a new identity with two new trig functions. And now we'll see something similar when we divide by sine squared. So I'll get sine squared divided by sine squared is 1 plus cosine squared divided by sine squared. Well, cotangent is cosine over sine, so this will be cotangent squared. And then last, 1 divided by sine squared. Well, cosecant is 1 over sine, so 1 over sine squared will be cosecant squared. So again, these are also considered the Pythagorean trig identities. And I can't say it enough. The more we understand about trig, the better off we'll be moving forward. But like I also said, unless you go to Calc 2, this identity kind of becomes a must at that point. But again, so many of the problems, knowing this one will be enough. But knowing this one means knowing its alternative forms. That this is its most basic, and that if we see sine squared plus cosine squared written together, that should become an automatic that we can replace that with the value 1. But the little modifications, that if you take this equation and subtract sine squared from both sides. The sine squareds would cancel here, so you'd only be left with cosine squared on the left side, but then you get the 1 minus sine squared on the right side. Similarly, go back to the original, but now let's subtract cosine squared from both sides. We'll still have the sine squared left on the left, but then we'll have 1 minus cosine squared on the right. These, I think, are important enough to definitely keep in our main list. And again, some people, this is enough, and these are quick enough direct results from this, but other people like to keep this in their main list. So now that we have our full list complete, now I'm going to just drop us right into the middle of a problem. I want you to verify the following trig identity. And I'm going to keep these directions for pretty much the rest of this video. Verify the following trig identity. Well, I'm going to start us off with one that's not too bad. We're going to start off with number 1, sine x secant x equals tan x. So what we need to start realizing, that when we say a trig identity, all we really mean is just an equation that contains the trig functions, right? So technically, a lot of people would argue that these first 4 are more the definition, but technically they're identities. Again, just equations that contain different combinations of the trig functions. But again, a lot of people, these are in some ways primitive enough that they are getting right back to the core of what is tangent, what is cosecant, and so on, so that people refer to them as definitions, but it has that fact. Can I use these facts and these facts down here to then prove that this fact is true? So by saying verifying the identity, in the reality, there are some books that try and say, is the identity true? And that makes a much, much more difficult problem. So to verify the trig identity, we should realize that this is a true fact, but it's up to us to prove that this is true. And the way to prove that this is true, we'll get some more details on this in a minute, but the real way is to pick one side. We can't work on both sides of the equation if we don't know it's a true equation. So what we will do is pick one side. Pick the more complicated side. Do what you can with it. So what does that mean? Well, sometimes that'll mean rewriting the functions in terms of sines and cosines. Sometimes that'll mean using algebraic properties to factor. Sometimes it'll mean combining like terms, finding common denominators. But that's the idea. And as we start getting through this, we'll start to notice that we can kind of get a good sense if we're on the right track or not. So, very, very rough guidance. But looking at this, technically I could start with either side, but if we start with the more complicated side, this one would be the left side just because it has 2 trig functions as opposed to 1 on the right. If we pick the more complicated side, things tend to work a little more smoothly. So I'm going to start off by picking my side. So I picked the left side. Now, ultimately, I'm going to just keep manipulating, modifying again, using algebra, using already known trig facts to keep manipulating, and I'm done when I get the right side. Again, everybody, this is what I was saying just a moment ago. This is not a guessing game. Does this equal the right side? It does. It's a matter of, can you demonstrate? Can you use your facts to get to that? Now, some of you in this first one, you might already see the key to this. This first one was a little light to get things started. So, but again, let's be very thorough. And the key to this is that you are doing a proof, so you really shouldn't be doing too much in your head. You really need to show me what you're doing. So I started with this side. Well, the first thing I can do, the sine is as basic as that's going to get, so I'll leave that alone. But secant, I can rewrite as 1 over cosine. And also, little things, everybody. Sine secant, what is the connection between these two? It's multiplication. If we saw the letters x, y sitting next to each other, we already understand through variables and through experience that's x times y. So this is sine of angle x, secant of angle x, but that's just having 2 things next to each other. That's multiplication. So sine times secant is becoming sine times 1 over cosine. I use the parentheses for times. A dot would be okay. An x is definitely not okay. We use x too often as a variable. Here I'm using it as an angle. Later on I'll go back and I'll use some thetas and things like that. But we really don't want to use x for a time, so parentheses if you need them. And now just start to realize how everything fits together. Well, you're getting sine times 1 over cosine. Hey, let's multiply that, and that'll just become sine over cosine. It feels like I've done everything I can, and look, I'm where I want to go. I wanted to finish with tangent. We've got sine over cosine. Tangent, by definition, is sine over cosine. Started with one side, kept working. Now in this problem, I just kept working to the left, but if I go down, whatever, however I do my path, that I started, and I just kept manipulating until I got to the other side. Okay, let's do a second one, number 2. And we'll still keep the second one fairly easy as well. Let's look at 1 equals tan theta, cosecant theta, cosine theta. Now, once again, these are still fairly light and easy to get ourselves going, but still good practice just to get us on the right track of what we're trying to accomplish. Now, this second one, well, one of the first things is just to realize we don't always start with the left. Oh, I'm sorry. Let me go backwards for one moment, everyone. Go back to number 1. I started with the left sign and went to the right, and I hope, especially with just a little bit of practice, that's a pretty natural situation. Just literally rewriting that as cosine, naturally doing the multiplication that presented, and hey, as long as we're paying attention, we got exactly what we wanted. But realize what would happen if you try to do that in reverse. If you start with tangent, well then you can write it as sine over cosine, but then you'd have to really be looking ahead to decide that's really the right next move. To arbitrarily decide, take sine over cosine and rewrite it as sine times 1 over cosine, that's strange. It's a lot more natural to take an expression like this and multiply it together versus taking an expression like this and pulling it back apart. So that's going to reinforce the idea, pick the more complicated side. So, in number 2, now the right side is definitely the more complicated side. So now we'll start with that one. So I've got my tangent, cosecant, cosine, starting with that side. And just like the previous one, the first thing I'm going to do is I'm going to get my stuff in terms of my sines and cosines. In just a moment after we do a few more, we'll give some guidelines. There's no set in stone rules as far as how to proceed through these problems, and we'll see in a couple of the more difficult ones, we can take some different approaches and still get the right answer, still have a good valid proof of the identity. It's just about, again, doing what you can. So, in this one, there's really nothing I can do the way this is written. My only real good option is to think about the sines and the cosines. So that tangent, well, that's sine over cosine. Cosecant, well, that's, again, all these are multiplied, so times now, and cosecant, that's 1 over sine. The cosine, well, that's already a cosine, so I'll leave that one alone. And I mean, maybe even up here, you want to write sine over 1. Maybe you want to write cosine over 1 here. That's your choice, but this is good enough. Because one more time, just like the previous one, as soon as we get to our sines and cosines, the natural things we can do pretty much finishes this problem off. That in this one, the sine in the numerator here would cancel with the sine in the denominator here. The cosine up here in the numerator cancels with the cosine in the denominator. So all that's left is 1, which is exactly what we wanted. Okay, but now let's start to move along a little bit. So now on page 2, same directions, we're still verifying the trig identities, but now let's start to take a little bit more of a jump. Let's next, sorry, one more quick thing before I skip past this. In problem number 1, the angles were x's. In problem number 2, the angles were thetas. That made no difference at all in the problem. I hope you realize that just when we rewrite things, well, when this was tan x, that came from sine x over cosine x. Well, here when it was tan theta, we had sine theta over cosine theta. the relationships don't change based on the actual variable that we're using. So some people, well, as soon as they get to this section, they just always use theta regardless of the letter that the book or that the letter that I give to you in the problem. That's fine, everybody, but just to realize it shouldn't really make a difference here. Okay, so now, back to problem number 3. Let's look at secant x minus secant x sine squared x equals cosine x. So what we've established so far is pick the more complicated side, and so far the more complicated side has always been the side with more trig stuff, more functions, more stuff going on, and that holds true in this one as well. But just to give one sneak little peek, if we ever have a situation with the same number of trig functions, pick the side with addition subtraction. You'll see why in just a few moments. So I picked the left side. So I've got secant x minus secant x sine squared x. And now the options start to present themselves. What do you do first? What seems natural? Well, this problem, we're going to get our first real alternative. Oh, and I'm sorry, I hate to keep going back, but just to realize number 2 is even worse than number 1. If you started with the right side, I'm sorry, what initially was the 1 was the left side, why would this make any sense at all? To arbitrarily just write sine over sine and cosine over cosine and break that apart. So one more time, even more so than this one, we almost had to start with this side to really make any progress, to really even get anything going here. And same thing, if you pick number 3 and start with cosine, what the heck are you supposed to do after that? There's nothing natural. But when you pick the side with a lot going on, that's when there are options that you'll start to see them, or when there are very few options, you'll at least have something to do. So, option number 1, what I've kind of been doing, let's get the sines and cosines in here. So secant is 1 over cosine minus 1 over cosine times sine squared. Okay, equals, I'll come down here now, I'll combine these two. So this first piece, this 1 over cosine is just being left alone. Here, sine squared times 1, the sine squared is on top, and a cosine on the bottom. Okay, equals, I'll finish this, just about finish this one up right here, because now, well, this still looks messy, but just the way things broke apart, I've got 2 pieces attached by subtraction, and they already have a common denominator. So I'm going to combine these as one fraction. The denominator is cosine, and the top will be 1 minus sine squared. Now you may feel like you're stuck a little bit, but that's where, again, that's where I was saying it's not just this main Pythagorean trig identity. We have to be just as good at spotting these alternatives. So I'm seeing a 1 minus sine squared, that can be replaced with a cosine squared. So right here, the 1 minus sine squared is now replaced with cosine squared. And look what's left. Cosine squared divided by cosine. Again, just like regular variables. If that was a squared divided by a, one a would cancel and an a would be left behind. So in that same way, 1 cosine cancels, 1 is left. Specifically, that 1 is left in the numerator. And that's exactly what we were aiming for the whole time. But like I said, that's one alternative. I started with the sines over cosines, just a little cleanup, naturally combined these 2 fractions, used a little identity, and then a little bit of dividing the similar terms, canceling those common terms. But an alternative. Start right here, still starting with the secant minus secant sine squared. But an alternative is someone might say, well, hey, look at that. These 2 big terms, they both have a secant in common. So they pull the secant out, and they're left behind with 1 minus sine squared. Now, there's that same 1 minus sine squared. And that's what I mean, everybody. Even when we have alternatives, we commonly end up using almost the same things. We just kind of sometimes see them in a little bit of a different order. So now the 1 minus sine squared, hey, that's the same as cosine squared. Let's try it. Let's see if that helps. So secant times cosine squared. And maybe it feels like I'm stuck for a moment, but now I realize, like, oh, wait a second, but wait, I could do more with secant, because I know secant is 1 over cosine. And now look, it's almost the exact same final spot. Literally cosine squared divided by cosine. Here it's 1 over cosine times cosine squared. But either way, we're still finishing with that exact same cosine. So, like I said, now we could take a little bit more time thinking about the generic guidelines. Our book gives us a little box, the bottom of page 570, and they basically say these same things. And again, everybody, it's not a set in stone process. It's mostly about doing what you can. They start off step 1, work with one side of the equation, typically try and pick the more complicated side. Keep the other side as your goal. Next, number 2, look for opportunities to apply the identities. What do they mean by that? Well, if the expression is a product or quotient of factors, consider the reciprocal and quotient identities. We're considering rewriting cosecants and secants and cotangents as sines and cosines. That's all that's saying. If square terms are present, see if there's any way to group them to use the Pythagorean identities. That's what we were just seeing right here. Apply other basic algebraic techniques, factoring, multiplying terms, combining like terms, combining fractions, using common denominator. Everything we've said, we've seen just by doing these first 3 problems. They finally, number 4, consider writing expressions explicitly in terms of sine and cosine. They kind of use that a little bit as a last resort, but again, we see so many of the identities rely on those. So again, it's all there. It's just trying to do what you can and keep working until you get something that is true. So let's finish this up. Let's do 2 more. Let's do 2 more that are, I don't want to say hard, but just a little harder. So let's look at number 4. And let's take a peek at, let's do cosecant theta minus sine theta equals cotan theta cosine theta. Same situation. Now we've got the same number of terms. 2 trig functions on the left, 2 trig functions on the right. Do the side that has the subtraction addition. It's easier to keep working here than it is here. And again, you'll see why in just a moment. So I'll start with the cosecant minus sine. First thing, nothing too crazy happens. Cosecant is just 1 over sine minus sine. That I can't do anything with. And very quickly, it feels like I'm a little stuck. So again, I started here, 1 move, but that's where the subtraction helps. The fact that these are being subtracted, I could write the second one over 1. I can get a common denominator. The common denominator would mean sine, so this one needs to be multiplied top and bottom by sine. So now I've got the common denominator sine. This already had a 1 minus, and now this will have a sine squared. There's that identity again. So that just became cosine squared over sine. And now you might think that you're stuck a little bit. And this is where, while we don't want to work on both sides, and again, I can't say that enough, everybody. There's a lot of people, they come to this one, especially when you get the one this hard. Now they want to start writing everything. That's 1 over sine. That's cosine over sine. And they're already cross-multiplying. You can't do that. You cannot treat it like it's an equation until you know it's already true in the first place. So, by starting with the subtraction, allowed me to get to here, but it still feels like I might be stuck. And this is where we have to realize it doesn't hurt to look ahead. If you started with the right side, what would your first move be? Well, it would probably be rewrite cotangent as cosine over sine, and then leave the cosine alone. And just thinking about that, even if you don't write it, and it doesn't hurt to write it off on the side, maybe down here, and then we'll connect the dots. But even just saying that, hopefully now we see how to finish this. cosine over sine times cosine. That's exactly what we have right here. Cosine squared is cosine times cosine, but there's only one sine. So put it in one of the expressions, the other is treated as over 1, and there's our cotangent and the cosine. Started with the left side, finished with the right. Okay, and one more, everybody. Just going back, start with the right side, very limited. Maybe you go to here, maybe you combine them, but making this move is weird. A lot more natural to take this ugly expression and to turn it into one term squared as opposed to going here to here. Again, there may, if you get far enough along, there may be a situation that you have to do something like that, but not really for our class. So, last one. Let's take a look at sine t over tan t plus cosine t over cotan t equals sine t plus cotan t. Now I've changed my variable from x to theta to t, and again, that doesn't matter. It's one more time. Pick the more complicated side. Now they both have addition, but now this has a lot more trig functions. So I'm going to pick this one. And the first thing is, as I pick that side, I'm going to write these in terms of their sines and cosines. And now I'll clean up. By having this ugly division, before I even think about combining the fractions, just looking at this ugly division, these are compound fractions. So thinking about this as, an a over b divided by c over d, that becomes a over b times d over c. Realize both of these, sine over 1, that's your a over b. So I get sine over 1 times cosine over sine. Oh, I'm so sorry, everybody. I miscopied. This is cosine t at the top. Sine t plus cosine t. Very similar over here. Cosine over 1, and then dividing by this, multiplied by the reciprocal. This time I just used my tiny dot. I just wanted to show you, some people don't like the parentheses. The dot's fine, just some people don't see it. If you make it a little too big, it looks like a minus sign. But now, I hope we see, we're ready to wrap this one up. Everything just naturally flowed. Converting to sines and cosines, taking care of things, good algebra, cleaning up these compound fractions, and it all works perfectly. Sines cancel. I'm left with cosine here. Here the cosines cancel. I'm left with sine. And I guess we could technically argue we've got one more line, realizing that cosine plus sine is the same thing as sine plus cosine, but just to write and show that. So again, good section. There's a few other ideas. They try and get you to work a little on your own just to try and clean up expressions, but verifying the identities. I would give you an identity. It is definitely true. So it would be a matter of, can you show it through your use of the previous trig functions and knowledge and use of algebra? Can you prove that equation is true?